Welcome everyone to a session on automata theory and computability. In this session, let us learn how to design a PDA for the given context-free languages. Before taking up any example, let us recall what we have learned in the previous lecture video. What is a PDA? PDA is a machine that is designed for a given context-free language, and it takes input which is a string, and decides whether the string is valid or invalid. So this depends on two parts of the PDA. So PDA is made up of two parts, that is an FSM and a stack, right? So on what basis PDA accepts the string? That depends on the following factor, that is the FSM should be in accepting state, okay, and the stack need to be empty. So after scanning the entire input string, so these two conditions need to be satisfied, right? The part of the PDA FSM which it should be in an accepting state, and the other part stack, it should be empty. Okay, so if both these conditions are true, then a PDA will accept the string saying that it belongs to the language. If either one of the cases is false, then PDA will reject the string saying that it does not belong to the language. So keeping this in mind, let us consider few problems and construct a PDA for the same. Let us consider this example. The language L is made up of string W from the alphabet set AB, and the definition of the language says A replicated n number of times, concatenated with B replicated n number of times, where n is greater than or equal to 1. Okay. So this problem is a context-free language because this requires to keep track of the number of A's and match it with the number of B's, right? So obviously cannot be done by using a simple FSM. So we need to design a PDA to solve this problem. Before writing a PDA, constructing a PDA, let us think about the approach to solve this problem. So for that, I will take one example that is valid according to the definition of the language. So I have taken AAA followed by BBB. So is this valid? Yes, this is valid because this has equal number of A's and B's. So in this case, it is 3 A's followed by 3 B's, right? Okay. Now, how we all know that at the end of the input, after scanning the entire input, the machine should be having its FSM in accepting state, and the stack need to be empty, right? And the stack is used to keep track of the number of A's and B's. So we need to perform push and pop operation on the stack based on the input symbol that is scanned in the input string, right? So for each and every character that is occurring in the string, we need to perform a stack operation. So what approach we can do? What we can do is, for every A, we can push A onto the stack, right? Okay. So for A, I am pushing A onto the stack. For the second A, so I'll push A onto the stack, right? And for the last A, I'll push A onto the stack. Okay. So after encountering 3 A's, this will be the content of stack, right? And what can we do while encountering B? For each occurrence of B, what we will do is, we will pop out the topmost element on the stack, right? So in this case, it is A. So for the occurrence of B, the content of the stack will be 2 A's, because I have performed pop operation. And for the second B, again we'll perform a pop operation. So the stack is having a single A, right? And for the last B, I'll pop out the last A that is present in the stack. Okay, so what we have done, we have performed push operation for the occurrence of A, push, and we have performed pop operation on the occurrence of B. Okay, so so what we have done is we had equal number of push and pop operation. So what will be the result of the stack? The stack will be empty. So this is true if the number of A's will be equal to number of B's, right? So then only the stack will be empty. So if I have more number of A's, then I will be having, then the stack will be having A's, some number of A's in it, right? So the element which is pushed onto the stack. And if I have more number of B's, then the stack will be having underflow, right? I'm trying to pop an element which is not present in the stack. So this will result in rejecting the string, right? Only if I have equal number of A's and B's, then the stack will be empty. Okay, so considering this approach, let us solve the problem. Let us construct a non-deterministic PDA based on the approach what we have seen previously, right? And there are techniques for reducing the non-determinism of the PDA that we'll be learning in the upcoming videos. Okay, so obviously I have to start with the transition diagram by writing a starting state which is named as Q0, right? Very similar to that of an FSM. And on the right part, let me write the content of the stack. So this will be the content of the stack. Initially it is empty. Okay, now being in Q0 state, can I mark Q0 as accepting? The answer for this is no, because if the string is empty, then that is not accepted according to the definition of the language, right? Of course, this will be having equal number of A's and B's, but the value of n should be greater than or equal to 1. So which clearly says there should be at least one A followed by a B, right? So this is the smallest length string that is valid according to the definition of the language. So epsilon is not accepted, so I cannot mark Q0 as accepting, right? Okay. Now let us consider this particular example AAA followed by BBB and try to write a transition, try to design a PDA for this. Okay, being in Q0, upon encountering A, so what shall we do? We will remain in the same state and we have to write a transition. So I'll be having a self loop. So Q0 upon A, okay, and what is the content of the stack? Stack is content, the topmost element of the stack is epsilon because stack is empty. And what do? We push A. Okay, yeah. So after encountering the first A, this will be the content of the stack, right? And this is the equivalent transition whatever I've written. Okay, being in Q0 state, upon encountering A, and if the topmost element of the stack is epsilon, then I'll push A. Okay, okay. What about the second A? Okay, so this is little tricky to understand, but I will keep the transition as it is. So yeah, now it is very easy to say the topmost element of the stack is A, right? But let us ask ourselves a question. So what is on top of A? What symbol do I have on top of A? I have nothing, right? So can I say that there is nothing on top of A? Yes. And nothing is represented by epsilon. So it is as equal of saying epsilon is on top of A, right? So can this transition, so is the transition true in this case? Yes, the answer is true. So now what I have is A, this is the input symbol A, and the top of the stack is still epsilon. So what do? We push A onto the stack, right? So this will be the content of the stack after encountering two A's, right? Okay, what about the third A? Okay, the same approach. I can say that epsilon is on the epsilon is on top of the stack, which is above A, right? And um, being in Q naught state, upon encountering A and top symbol is epsilon, I can push A, right? So I'll perform again push operation. So this will be the content of the stack after encountering 3 A's. Okay. Now we will encounter B. So when I encounter B, I have to make a transition to a different state. So I cannot remain in Q naught, because if I remain in Q naught, there is a possibility that A will occur after B, right? And that should be totally rejected. So upon encountering of B, we have to make a transition to a different state. Okay, and let me name it as Q1. And what is the content of the stack? Yeah, on the top of the stack I have A, and what we have to do, we have to perform pop operation, right? So being in Q naught, upon encountering B and topmost element is A, I'll do pop. So this is pop, right? So what will be the content of the stack? Content of the stack will be, when I perform pop operation, the topmost element will be popped out, that is A will be popped out, right? Okay. Now I'm in Q1 state. Okay. Now what transition we have to write? In Q1, being in Q1 state, I have to encounter only B, right? So if you encounter B and the topmost element, if it happens to be A, then you perform pop operation. Okay. For the second B, yes, so A will be popped out from the top of the stack. So I'll perform pop operation. Okay. So this will be the content of the stack after encountering AAA, BB, right? Now for the last B, again we'll remain in Q1 state and we'll perform pop operation. Okay. So after encountering 3 A's and 3 B's, the content of the stack is empty, and I have to mark Q1 as accepting, right? So Q1 will be the accepting state. So after encountering the entire string, the PDA has ended up in Q1 state, which is the accepting state, and the stack, content of the stack is empty, right? And these are the two necessary conditions for a PDA to accept a string. So what I can say, the string is accepted, right? So this is how we solve the problem by constructing a PDA for this particular language, right? Okay. Okay. Now let us take an example of a string which is having uneven number of or unequal number of A's and B's. Okay, so I'll take 2 A's followed by 3 B. So what will happen? So for this, being in Q naught state, A will be pushed onto the stack, right? And for the second A, again I'll push A onto the stack. And while encountering B in Q naught state, a transition happens to Q1 state and A is popped out, right? So A is popped out. So this is after encountering first B. And for the second B, again another A is popped out. So this will be the content of the stack after encountering 2 A's and 2 B. But we are not done scanning the entire input. So for the last B, being in Q1 state, there is no definition when the stack is empty, right? I don't have a transition in Q1, so I don't have B upon epsilon and what need to be done, right? So this is missing. So when I don't have a definition for such kind of transition, the machine will not be knowing what to do, right? So it will halt and the string will be rejected. This string will be rejected. Okay. So if we have more number of A's, let us check what if I have more number of A's. So in this case, 3 A's will be pushed onto the stack, and for the first B, A will be popped out, okay, and for the second B, A will be popped out. Now the machine has ended up in Q1 state, which is accepting, but the stack is not empty, right? When the stack is not empty, after scanning the entire input, the string will be rejected. Okay. So this is how the PDA works. Of course, it is a non-deterministic PDA, and we will be designing a PDA by considering only the path that will lead us to an accepting conditions, where the string, where the FSM ends in an accepting state and the content of the stack is empty. And let us write the tuples for this particular PDA. Let us fill all the tuples for this particular PDA. Start with K. K, as it represents the set of states, which is nothing but Q0 and Q1. Then sigma, alphabet symbols that are used in the definition of the language, which is A and B. Tau, stack symbol. Here we made use of A as a stack symbol, right? And it is not necessary that I have to take a stack symbol from the alphabet set sigma. Okay, I could have used it X or any other symbol, but for the sake of simplicity, I took it as A, okay, which is one of the symbols in the alphabet set. Next is starting state S, which happens to be Q0. A, set of accepting states. Here we have only one, which is Q1, right? And finally, we'll write delta, which is the transition. Okay, so it's a set of transitions. So being in Q0 state, upon encountering, so we'll write all the transition that is defined in the PDA. Okay, Q0 upon A, and what is the pop operation we do? We don't perform any pop operation, so this will be epsilon, and we make a transition, will be in Q0 itself by pushing A, right? Okay, so this is one transition, and the other one being in Q0 state, upon encountering B, we pop out A, okay, go to Q1, and we push nothing, right? And finally, being in Q1 state, upon encountering B, pop A, remain in Q1, don't push anything, right? So this will be the content of delta, which is the transition relation. Okay, so with this, all the 6 tuples of the PDA is complete, right? Okay. Now let me take a small variation of the previous problem. The only change is value of n is changed to greater than or equal to 0. Okay, so the smallest valid string is epsilon, right? Since when value of n is equal to 0, the number of A's and B's will be equal to 0. So I'll get epsilon, which should be accepted according to the definition of the language. Okay, so let us draw a PDA for this. Okay, so Q0. Okay, so initial stack content will be epsilon, right? So, and if you encounter 0 occurrence of B, A, followed by 0 occurrence of B, so that is A0, B0, I'll get epsilon. I should be able to accept this, right? So I'll mark Q0 as accepting state. And do I have stack empty? Yes. So I am in as Q0, which is accepting, and the stack is empty, so this will be accepted, right? Okay, And if I have at least one occurrence of A, then I should have one occurrence of B, right? So what I can do, I can make a transition. So the same transition what we have encountered in the previous problem. I'll push A, right? If I get B and top of the stack is A, then I'll pop. Okay, and go to state Q1, which is again marked as accepting. And being in Q1, if I encounter further B, I should pop A out, right? Yeah. So this will be the changes that I need to incorporate if the problem is given as n greater than or equal to 0. Okay, and the value of the tuples will also change. Yeah, the only value that changes is A value, right? So K will remain as Q0 Q1, then sigma will remain as A and B, then comes tau, which is A, starting symbol S is Q0, and A, which is a subset of K, will be Q0 and Q1, since both Q1 and Q0 are accepting, right? And finally delta, which is equal to Q0 upon A, no symbol to pop, remain in Q0 by push A, right? And Q0 upon B, pop A out, go to Q1, push nothing. And the last one, being in Q1 upon B, pop A out, remain in Q1 by pushing nothing, right? So this will be the transition, this will be the content of the tuples for this particular PDA, the content of 6 tuples. Okay. So I'll see you in the next one, where we will be looking into more such problems on context-free language.